Okay, so in this video we'll talk about quantum complexity theory. Now, quantum complexity theory is a vast subject, and you shouldn't expect to learn a lot about it in a 15-20 minute video. So think of this video as a taste of quantum complexity theory. It'll try to give you a picture of what the basic quantum complexity class is and how it relates to classical complexity classes. Now, of necessity, this is not the lecture that I expect you to understand in detail. So just think of this as something that'll whet your appetite, give you a picture of what quantum complexity theory is all about, and if you don't follow it, don't worry too much about it. Okay, so let's start by a brief introduction to classical complexity theory. So let's first talk about what a computational problem is. So a computational problem is something like you're specified some input-output relationship, and you want to try to achieve this input-output relationship via a suitable algorithm. Okay, so here are examples. So you might want to multiply two matrices, M and N, which are given to you. You might want to test whether a given number is a prime. You might want to solve the related problem of actually producing a prime factorization of a given input number N. Or you might want to test whether a given Boolean formula F is satisfiable by actually producing a satisfying assignment X. Okay, now we say that a given computational problem is solvable in polynomial time if there's a algorithm which on inputs of size n halts in time order n to the k for some constant k, meaning it halts in time some bounded by some polynomial in n, and it outputs the correct answer. Now, in this course so far, we've been talking about circuits. So the corresponding statement for circuits would be that on inputs of size n, you have a circuit C which takes inputs of size n and outputs C of x, which is the correct answer to this problem. And the running time, instead of running time, we'll talk about the size of C. So we'll say, saying that there's a polynomial time algorithm corresponds to saying that there's a family of circuits C sub n, one for each length n, such that on inputs of size of length n, C sub n outputs the correct answer, and moreover the size of C sub n, the number of gates in C sub n, is bounded by some polynomial in n. There's also some sort of uniformity condition which says that the circuit C sub n can be efficiently computed given n as input, but we won't get into the details of these definitions. Okay, so now the class P, or polynomial time, is a class of all computational problems with polynomial time algorithms. So in our example, matrix multiplication is polynomial time solvable. It's in the class P. But we don't think factoring is, and we certainly don't think satisfiability is. What about primality testing? Well, primality testing is sort of, it comes very close to being in the class P. What it is in is the class BQP, which corresponds to polynomial time for a randomized algorithm. So here's what we mean by that. What we mean is that there's some circuit which takes as input x, but it also takes as input some random bits r. And now what we want is that C of xr is the correct answer with high probability. So we might say, well, it's correct, say, with probability at least 3/4. But now if we want to boost the chance of success, all we have to do is run this circuit many times with independent random bits and take the majority answer. And we can boost this success probability from 3/4 to something arbitrarily close to 1. Okay, so our mantra is that polynomial time is good, exponential time is bad. Why is exponential time bad? Well, we've seen this already. Exponential time grows so quickly, the exponential function grows so quickly that already for even small values of n, exponential in n is larger than number of particles in the universe or age of the universe, and that cannot be a good time bound. Okay, so that's our basic distinction between polynomial and exponential. Now there's a question that we've begged, which is, how did we decide our model of computation? Why was it circuits or Turing machines or algorithms? How did we decide what model we are going to run our algorithms on? And this is a very important consideration. This is what the foundations of complexity theory are built on, and it's called the extended Church-Turing thesis. What this thesis asserts is that it doesn't much matter what your model of computation is. Your running times will work out to being essentially the same, to within polynomial factors. So if you're talking about polynomial time computation, it's robust against changes in the model of computation. So this is another reason we like polynomial time, because it's a robust notion of running time. So what the extended Church-Turing thesis actually says is that any reasonable model of computation can be simulated on a probabilistic Turing machine with at most polynomial simulation overhead. What does this mean? It means, for example, that if you have a running time of t steps on some model of computation that you've invented, which you think is reasonable meaning you can implement it in principle, physically implementable in principle, then you can also run this algorithm, say in order t squared steps or some polynomial in t steps on a Turing machine, on the simplest model of the model. Now, where does this extended Church-Turing thesis come from? How do you interpret it? Well, one interpretation for this extended Church-Turing thesis was that a Turing machine describes the set of all functions that are computable by a mathematician. So you think of the Turing tape as being an infinite supply of paper. And you think of the finite state control as your mathematician, and the read-write head as a pencil. So you have a mathematician armed with an infinite supply of pencils, an infinite supply of paper, and you want to know, what can this mathematician compute? What are the functions? What are the problems that this mathematician can solve in a reasonable amount of time? Well, that's what polynomial time describes in this one interpretation. The second interpretation of this thesis is that the class polynomial time represents what can be physically computed in this universe in a reasonable amount of time. And the rationale for this is that Turing machines can simulate cellular automata with polynomial overhead. Right? They are polynomially equivalent to cellular automata. And somehow the argument is that cellular automata represent everything that you can compute in the classical universe. Okay, remember, we are talking about classical complexity theory so far. So why is it that a cellular automaton, by the way, this is a cellular automaton that's simulating what's called the game of life, right? Conway's game of life. Okay, so what is it about a cellular automaton that makes it such a convincing model for anything that can be computed in the classical universe? So in a cellular automaton, each cell looks at its small neighborhood, the cells around it, and its new state, it's in one of a finite number of states, and its new state is a function of its, the states of all the cells in a small neighbor, its neighbors. Okay, now this is directly analogous to something in physics. It says that, so classical physics is described by local differential equations. Which means that what you're saying is that, if you want to know how some quantity changes over time, electricity, magnetism, whatever, then what you have to say is that, the value of that physical quantity at a certain point, at t plus delta t, is determined by sort of, that point just looks at an infinitesimal neighborhood around it, and based on the value at time t in this infinitesimal neighborhood, you can determine the value of at this particular point at time t plus delta t. Okay, but now, so you can see that cellular automata these are discretizations of local differential equations. And you can argue that if you want to compute, then your computer has to be fault tolerant, that it cannot be that you assume infinite precision in your model. And so you have to discretize it, you have to have a digital abstraction. And once you take your local differential equations and you subject them to a digital abstraction, you get cellular automata. So that's the argument that polynomial time is the limit of what you can compute in the physical world, classically. And so quantum computation is the only model of computation that violates this extended chair Turing thesis. It's the only reasonable model of computation which cannot be simulated in polynomial time on a Turing machine, on your classical Turing machine. So what's our evidence for this? Well, we have two kinds of evidence that it violates the extended chair Turing thesis. One is our black box separations. So we already saw these examples of algorithms, such as the recursive Fourier sampling problem or Simon's problem, where we said there is no polynomial time. You can solve these problems in polynomial time on a quantum Turing machine or with a quantum circuit, but there is no corresponding polynomial time solution to these problems classically, using a classical algorithm. We also saw that there are problems that we strongly believe to be difficult classically. In fact, we believe that we believe this so strongly that we base cryptography on them. These are problems like factoring and discrete logs. And for these problems, we know that there's a polynomial time quantum algorithm, but we strongly believe that it takes exponential time to solve them classically, or at least all the algorithms that we know of so far take exponential time. So these are the two kinds of evidence that we have that quantum computers violate this extended Church-Turing thesis. Now you could ask, why are we messing around with this kind of evidence? Why don't we just flat out prove that quantum computers violate this extended Church-Turing thesis? Well, the answer has to do with this. Okay, let's first define this class BQP, or bounded error probabilistic polynomial, quantum polynomial time. Right, it's the class of computational problems which have polynomial time quantum algorithms that output the correct answer with high probability. So for example, factoring belongs to BQP. Now, okay, so you can show this inclusion that P, polynomial time, is in BPP, probabilistic polynomial time, which is contained in BQP. So BQP is this class that we are interested in showing is so much larger than P or BPP. But then you can also show further containments. You can show that this is contained in something called P to the sharp P, which is contained in P space. P space is a class of problems that you can solve using not a polynomial amount of time, but polynomial amount of space. So you can if you have only a polynomial amount of memory in your algorithm, but you can keep reusing this memory, well, then that's P space. Now the interesting thing here is that P versus P space, whether or not P equal to P space, this is one of the major open questions in complexity theory. So this is an open question in complexity theory. We strongly believe that P is not equal to P space, but we don't know for sure. We don't know how to prove it. So now you can see, if we could show that BQP is strictly larger than P and BPP, then we'd have shown that P is not equal to P space, thus solving this major open question. And this is why we have to deal with this sort of evidence that BQP really, that quantum polynomial time is larger, that quantum computers violate this extended Church-Turing thesis. Now what's sharp P? Well, sharp P is the so-called counting class. It's a complexity class having to do with counting. So let's say you have a circuit. So you have some function f which maps x and y to f of xy. Okay. Now we can define a counting problem associated with this. We can say the count of x is the sum over all y of f of xy. You see, so what this is saying is, if you were given x and y, you could of course compute f of xy quickly, because f is implemented by a polynomial size circuit. But now what you want to do is you want to sum up f of xy over exponentially many different y's, and this is now a much more complicated problem. It turns out that if you could solve this problem, then you can actually solve, then you can simulate any quantum computation that you want. And the way you reduce a quantum computation to this sort of counting problem is, it's reminiscent of Feynman's path integrals. So in fact, in some sense, what Feynman came up with was a way of showing that BQP is in P to the sharp P. It's actually not a very difficult proof. It's a simple proof, but I really don't want to get into this now. It's, we don't really have the time, and it wouldn't be appropriate. We couldn't really do it justice in this sort of setting. Okay, so now we could try to understand, our complexity classes a little bit better. So here we have P, or polynomial time. And then remember, there was this class NP, which contained many of the problems that we'd like to solve, like satisfiability. Now, if you take a problem which is in NP, like satisfiability, you could also look at the complement of it, and you get this class CoNP, which contains problems like not satisfiable. Is this formula not satisfiable? And then it turns out there's a high, so there's an infinite hierarchy of such classes, NP, CoNP, what's called sigma 2p, etc., pi 2p, etc. And these, this entire class of problems sort of forms what's called the polynomial hierarchy. And all this, this entire structure sits inside p to the sharp p, and which finally sits inside p space. So now you could ask, well, we've already said that we believe that BQP, that you cannot solve the NP complete problems. So the problems right here, we cannot solve them in polynomial time. In polynomial time on. So this is, let's say, the NP complete problems. And we believe that these cannot be solved in polynomial time on a quantum computer. Right? So what does this class BQP look like in this picture? So is it contained inside of NP? Well, we already have a hint. What the hint that we have is that this problem, recursive Fourier sampling, we can show that in a black box model, this does not belong to MA, Merlin-Arthur, which is a probabilistic generalization of NP. So it lies outside of this NP, but not only does it lie outside of NP, but it even lies outside a probabilistic generalization of NP. We can't show this, like all of these results, we can't show this unconditionally. This is in a black box model, or also called an oracle model or setting. Okay, so now what should we think about BQP? So the idea is that BQP somehow, it doesn't contain the NP complete problems. It instead is some sort of complexity class which heads out like this. And it contains recursive Fourier sampling. And how far it heads out into this whole thing, we don't quite, we don't yet understand. So we could ask, how far outside of NP are these problems that BQP might contain? And could it be that, in fact, it even extends outside of the polynomial hierarchy and contains some problems out here? And the conjecture, which is very long-standing, it goes back almost 20 years, says that, in fact, the Fourier sampling problem should be one such example, which is not in the polynomial hierarchy. This has proved to be remarkably hard to resolve. And a few years ago, Scott Aronson came up with a simplified problem, which he conjectured is also not in the polynomial hierarchy, but which can be solved in polynomial time on a quantum computer. And this is called the Fourier checking problem. So here's a pointer to a paper that discusses this problem. But it's actually a very simple problem. It's very simply stated and very elegant. So let's say that V and W are random unit vectors in real n-dimensional vectors, where capital N is 2 to the little n. So these are exponential dimensional real vectors. And now, given such a real vector, you can think of it as defining a Boolean function. Okay, it's a function which, so in other words, you have this exponential dimensional vector where each entry is a real number. So this real number, let's say, is r sub k. And now you could think of this as defining a Boolean function for you, where it maps k to the sign of k. Right? So it maps an n-bit number to +1 or -1. Okay, so now since you have two such vectors, they define two different functions, f and g, which are Boolean functions on little n bits. So what we want to do is distinguish. So we are given two such functions. Either we are given f equal to sine of v and g equal to sine of w. The sine functions defined by these two random vectors, or we are given f equal to sine of v and g equal to sine of hv. So instead of w, we now use the same vector v, once as it is and once having applied the Hadamard transform to it. And we want to be able to distinguish these two situations from each other. And the point is that there's a very simple quantum algorithm that will distinguish the first situation from the second one. But the conjecture is that you cannot do this distinction anywhere in the polynomial hierarchy. Okay, so I should mention that this is one of the central open questions in quantum complexity theory, understanding the power of BQP, quantum polynomial time, and this is completely wide open as we speak. Okay.